Okay, now the next step in our examination of this inheritance idea is to set up a situation like this. Now what I'd like to do, or my goal here, is well, first getting rid of all this stuff. We can get that back later if we need it. Let's get rid of food. I'd like to keep that. And one of the things that I've been trying to do, and I guess this is good enough, is you'll notice I dropped the dots here, and the reason is I can no longer put the dots, and the reason for that is because I put main here in this common lib, which calls another function. This looks like it's main, but it's not actually main. It's got yet another underscore in front of it, and this is not a C declaration. It's CPP, so I can't just arbitrarily put ellipsis at the end. Here's the actual call. In the actual call, there is a little bit of lying going on. I am passing that environment pointer on to the stack, to this underscore main, even though it's declared as having only 2 arguments. And actually, if you look here, there is a reason to do that. I mean, there is evidence here in the runtime library that 3 arguments are pushed on, so I'm confident that I can put these 3. Now this is the actual main. I can put anything I want here. I could add more and more stuff as long as I want. And that trick, however that works, I can't figure it out. It's how it's possible that I'm declaring this in a C++ file, and yet the exported function, this exported function, doesn't come out as a C++ function. I mean, forget about the T there. This translates to main, okay? This is sort of a diversion, but I'm very curious, and if anybody knows the answer, I wish they would come forward and explain it to me. Symbols. Now it's in common lib. Just look for the symbol main. See? Now, here's this underscore main, and here's a double underscore main. Where is that? That's certainly not this one. That isn't declared anywhere. Int, taking int, and one pointer. But that's it. Well, okay. I'm saying that there's an import, an extern, I suppose, they put everything external. Oh, okay, undefined. Undefined, that's one. It's not in the file. That's the one that it's going to call. This one is defined. Section 31, offset 130, is a C function called main. Now, how do they do it? How in the world do they do it? I don't know. Because if you declared in a header file, for instance, that this was a C, that there's a C function by this name, right? And then I tried to write it down in here, I would have to give it the same specifier. I would have to write extern C ahead of this, but I'm not writing extern C in front of here. Why isn't it doing what it's supposed to do? It's really a mystery, and I can't figure it out. But so from now on, I have to give two arguments. Even though I never I never use this one. I haven't used this one in years, but I only ever use the first one. Because when you have the first argument in this function, you can get the second and the third just using some variable argumentless macros that already exist. So you don't actually need to specify anything here. In any case, here is what we had. Now here's the C++ way. A inherits from B, B inherits from C. So here's a situation where there's a hidden B here, yet inside of B there's a hidden C here. And I've calculated these sizes. C actually turns out to be 56. Yeah, 56 bytes in decimal, and I think that's 38 hex. That would make sense, yeah. Add 8 to 48, and you get 56. Now, well, this is a guess, right? This is an unknown at this point, although it should be pretty obvious that it's going to be the same, given that these are both multiples of 8. So we're going to be at the same 8-byte boundary when we hit A, and so there's going to be an extra 6 bytes unfilled. Whether or not the memory is laid out this way is something we have to prove. And not only that, I would like to see if that's the way it would be if we did it in C. So let's try the C way first. We know it works for B. Get rid of that. Get rid of that. And we're assuming that B contained a C. So in theory, this should be the same situation. So for instance, we could print out size of A. I changed the font on here, by the way, in case you didn't notice, to try to make things clearer. In fact, I had this over here for some more vertical space, which is fine. I can put it back when I need it. Size of A. Now, according to theory, in either case, since the struct alignment is 8, there's no extra padding or anything for these two structs. And so we should get 56 is 7 times 8, and 48 is 6 times 8. So how do you like that one, eh? Clear the screen and I'm still on the bottom. What do we got here? 56 plus 48, and it should be plus 8. So this total size should be 112 with 6 wasted bytes. Here's my output. What am I doing here? $112. So we're okay on the size. Now what I want to know is I'd like to print out the addresses of the various members. So let's print those out too. Address of A, C, that's the expression I want also, and also B. Oh, and also the address of, well, no. The address of A, it's the A structure, will be the same as the address. It should be the same as this. So we can insert. We can print what looks like an assertion. According to the explanation I gave before. That the first variable's address is the address of the struct. So these two should be the same. And the printout will show us that or not. Okay. So indeed, those two addresses are the same. The address of C is here, 94, and V is that. And I can take that difference grab these numbers. I was doing this before, that's why I have my things set up. So I guess decimal would be easier to look at. So B minus C. B minus C. $56. So that's correct. There's a 56 byte difference between here and here, and I could also, if I wanted, print the address of A's other member. This one doesn't really have much meaning until we do the inheritance bit. So that it should come out as it did before. That is, the address of B plus size of B should give address of SH. So that's that. Okay, so here's our results. And let's see what this difference is. Should come out to be 30 hex. So we're doing hex. Address of sh minus address of B 30 hex. So no mysteries there. Now I've actually been going through this, and I did a whole video and deleted it because something came up and I wanted to work it out. I don't know if I just mention. Yes, I did mention that these are multiples of 8. Now, if struct member alignment is by 8s, that means if I add anything to this, like just add an extra character, that should add another 8 bytes to the size of C, and that should increase the size of the whole struct by 8 bytes. So let's see if that's true. Now it's bigger by 8 bytes. Well, what about our differences? Well, these two are actually the same address, it turns out. Notice that? The address of that is the same, and the B is the same, but C, which is really the one furthest lowest in memory, right? The reason why people write memory increasing downwards, that is, higher addresses as you go down, is arbitrary. I mean, there's no logical reason, but there's a practical reason. And the practical reason, I think anyway, is that if you're reading code and you're going line by line through your code, you're imagining that you're increasingly moving along in memory, but you're going downwards. If you thought of memory as increasing in an upwards direction, then you would write your code at the bottom and have to write each consecutive line above the next in order for it to be flowing in the direction of the instruction pointer. So it's more natural to look at it this way. Now what's happened here is this has gone down, and so now let's see, that is the smallest number. So I'll put that at the end. And so the distance between the base position of B And the base position in hex anyway, let's try decimal, is 64 as is sort of expected. So now we added 1 to this. That became a 39. This jumped up to 64 for the size, whereas there are only 57 bytes of data. For this particular struct, or part of our whole structure. Now that's weird. That means there's a hole. There's a hole between B and C and B, and it's definitely a hole. It's not like you'd think that what it could have done is shifted B up 7 bytes, fill in the gap, so that it all remains continuous. But it doesn't. It gets a hole. Now I discovered that the same thing occurs in C++, and I'm happy to see that it's the same in C. So that means that we haven't, nothing unusual has happened. The holes that we usually get in C follow through in C++. Alright. Now, so we solved the layout. Now I'm curious about the construction and the destruction of these objects. Now, if you think about it, you don't even have to go through the experiment, but I'll do it anyway. Certainly, if I've declared one of these A's, okay, and I won't declare it in my phony main, I'll declare it in another function. Call that instead. I don't want to have to leave this scope to see it complete. If these had constructors and destructors, they would be called, okay, at least a default. And so what I've got is a macro I made with my macro. Macro. Where are we? That's almost it. Default constructor. Well, let's leave it down here. No. Default constructor for an object of type T. Just that would stay. In order to create one, if you have the double-clicking feature on your computer, it's just that. Okay, so what this the replacement gives you is C bracket bracket, put a string, and then the function name. What I would like to add to that, well, change this to printf so I can add the address. This is the function name. Pointer value. Now, in order to get the address of basically the C subsection of our entire class, we use that trick. We'll take the address of the first member, Now I can't generalize that bit. I'll have to pass some kind of argument in here. Let's call it the zeroth member. This member 0, not member. R0. Okay, so in this case it would be stir, for instance. The address of stir will be the address of a C structure. Okay, structure of type C. That's the constructor part. I'm going to print it out. And I can, in the same macro, I can define a destructor, which I will. And that one will just do print the function. Okay, default constructor, also destructor, condef. Let's put one in each. This is a B, and its first member is D of 0. And for A is the name of the whole of the entire structure. However, what I want printed out here is not the address of the A struct, but the address of the subsection of the entire structure, which is an A type structure. And that's what this macro will give me. Okay. Now all I got to do really is just step over this. Have a look at the output. First, you'll notice that the construction order was in the order I had suspected, which makes perfect sense. If you were in A here, that has B as a member, even if this were in C, and if there were constructors in C, your members would have to be initially constructed before the last bit, the A part, can continue with its whatever it needs to do to construct itself. One part of which might be to change D of 1, let's say. You know, it always wants to set that to some value. If A happened before B, then B would overwrite A's alterations. So since A depends on B, B has to be built before A, and in similar manner, B depends on C, so C has to be constructed before B. And it also follows that if there were a default constructor for the string object, that would have to be done before C's constructor gets called, and so on and so forth. There's a definite order. Destruction necessarily must happen in the opposite order, like pushing and popping. B doesn't know anything about A, but A may need something from B in order to decide how to destroy itself, or what to do when being destroyed. So B must not be destroyed before A. A first. It depends on B, and then B before C, because, again, B depends on C. So we must make sure that C doesn't die before B. So all of this makes perfect sense. And the addresses are not the same ones that they were, or are they? Well, part of it's similar. C happens to be, for some strange reason, has decided to keep its last address, 8C, but these have shifted down by 8 because I got rid of that little character. I guess if I added it back, I might get the same. I might get this one back. I didn't print the size here, did I? That's something easy to work out. 8, no, it changed. Now it's on to 8-4. There's no reason to suspect the same addresses every time. But, again, oh, I see. Well, again, in the C++ case, the A and B retained their addresses, and C was pushed down in memory, up in direction, but lower in memory. And I'm not sure if that's a part of the standard or not. That just happens to be the way it works. Okay. Alright, so now we know a little bit about how this kind of inheritance chain is organized in memory. We know that there can be gaps. We can't think of this as a continuous continuous flow of structs. There may be holes and gaps depending on alignment, but that shouldn't matter because if I'm trying to pass this A object to a function as a C, right, then it can compute the proper offset, and this is a C. If I try to, this part is a C. Similarly for B, it'll be a different, maybe a different offset, but the type is correct. The fact that A has those extra bytes in it that don't do anything is of no importance. Now, I wanted to do something, and it's kind of interesting. Just a minute. But I don't have time to do it. Let me just give you a glimpse, if I can find it. Alright, too much of this junk. Oops, I wanted to keep that one. Where'd it go? Oh yes, here we go. What I'm going to do, this isn't the final version of it, I don't think, is well, I've given these things constructors that do things, and let's see now. Well, actually, we've actually done most of this stuff already. But there's some things like what happens when you copy and so on, and how does the memory get copied? But I guess we looked at that too. Maybe I can skip this bit. Okay, we'll skip that bit. Now the next step, which I can't go into yet. We've seen this now. I don't know what the name of our C file. I don't know what the technical name for this is. I don't remember technical things. But I would call this, let's say, linear single inheritance. That is, we're inheriting from an object that inherits from an object, and so on and so forth. Okay. Now that's one way that an object can inherit the properties of another object. But there's another kind of inheritance method where C and B are not related. Okay, so it's a scenario like this, but I still want my A, for instance. I would like to obtain additionally the properties of C, and that type of inheritance works like this. So here we have a struct A that has acquired B through inheritance and C through inheritance, but not in this linear fashion. B has no relation to C. Okay? So this is kind of like a sideways type of inheritance. And this is called, this one I think I do know the name for, multiple inheritance. So that's when you have an object which inherits from two different objects separately. It didn't acquire C by accidentally, inheriting from B. The way it acquired the C bit in the first case was, in a sense, unintentional. If A just wanted to become a B, it just turned out that B was a C. In the second case, this is A deciding I want to be a B and I want to be a C as well. I want all of C's data and all of B's data, and if there were functions, I want their functions, and so on and so forth. And now the question is, in this scenario, what would be the layout of the memory? What would be the order of construction? Left to right, right to left, and destruction. And as a further, possibly last thing to look at in terms of all possible cases, if there were one more struct with whatever members, and let's suppose we have something like this. Okay, now we got a situation where B here is also a D. So there's kind of, you can think of, I don't think I can draw an arrow with this font. 25. Oh, I can. There we go. So this is kind of going this way. 24, 20, 27. There we go. This is kind of a situation like this. Where the B is going in to A, and C is going into A kind of sideways, but D, well, maybe I shouldn't draw this arrow. And I don't know if this is, maybe it should look that way. Anyway, as you, the interesting bit about this is how is something like this going to get laid out in memory? We certainly know that B and D are going to be connected somehow. They'll probably be aligned in memory. C could be off on the side somewhere. And we can probably say that D would be constructed before B. B and C are independent, so their construction order is semi-independent. All these things have got to get done before A can be constructed. And then there's the layout in memory. How does that work? Is there a general rule that we can learn to know how everything would be laid out in memory? And I think there is. And once we know that rule, then we don't have to think about these sorts of problems anymore. We can just know the answer. And I'm not sure what the standard is. We see, because is there any other possibility? Because it's possible to add more stuff on the side here. And it's also possible that there are weirdo possibilities. Like, you could have C here, which maybe depends on another object. Call it F, okay. And maybe, can I make a crooked arrow? Not really. Well, imagine, oh yeah, that works. Okay, perhaps you have a situation like this, where both of these objects are inherit from the same object, okay? And then these things might inherit from those objects that inherit from the same object. Are we going to get two copies of that common object? You see what I mean? Like, once you can go sideways and this way, it's like it's a two-dimensional problem instead of a one-dimensional problem, and the memory layout becomes difficult to address, to say the least. And that's why one of my rules of programming that I try to adhere to is to, as much as possible, avoid multiple inheritance. Try to stick with the linear inheritance if you can. That's easy to understand, and you're not going to make a mistake. Things like this, okay, although it might be interesting and a fun puzzle if you're a mathematician or something, in the programming world, we don't want puzzles. We want solutions. The best solutions are generally the straightforward, easiest one. And if you end up with a situation like this, where it's confusing, stop and think for a minute and say, well, maybe we don't need G. We'll just get rid of it and try to just use this object and make something else that doesn't depend on something that gives us a two two objects that share a common ancestor, something like that. Eliminate bugs by eliminating complexity. Okay. So, in fact, I may not even go over that scenario because I advise ever getting into that scenario. Never getting into that scenario. Okay. Alright. Well, I'll continue on with this later. There's much more to this inheritance story than what I'm telling you here. Even with the simplest case. Because we haven't talked about the functions yet. How do the functions inherit? And that's when it starts to get interesting. And that's when what was the word that I was using all the time? Not polymorphism, but that's when this abstraction idea starts to come into play. Is when we add the functions. Okay, so we're getting to that, and that's really, really interesting and cool. So I want to get there as quickly as possible. Okay, see you soon.